Hello and welcome everyone. This is Manish from Skillable India. In today's session, we are going to learn about the very important geometric tolerance, which is the positional tolerance in the geometric dimensioning and tolerancing. Okay, so now we are going to discuss about the positional tolerance. Okay, one of the first, I will say, geometric tolerance under the location control. So first of all, we are starting from the location control. This is the first tolerance, which is the position tolerance. This is one of the most important geometric tolerance out of all the 14 geometric tolerances. Okay, so in this discussion, for the positional tolerance, first you have to be understand totally about the coordinate tolerancing system. So I will recommend you to just go through with the my session, which is I have conducted on the coordinate tolerances. Okay, so now we have to start with this. Okay, so we are going to start with the definition. Okay, so true position or just a position as per the ASME Y14.5 standards calls it is defined as the total permissible variation. Okay, here from the total permissible variation that the feature can have from its true position. Okay, so this position means that the total permissible variation, how the feature, in this case I will consider a hole as a feature. Okay, so if we considering hole as a feature, so a hole is what type of total permissible variation of that a hole can move from its true position. Okay, let's say if I am making here one part. Okay, and this is a hole inside that part. So in this definition, it is trying to say the total permissible variation. So the total permissible variation is for this hole. Okay, that a hole can have from its true position. Okay, so let's say this is the true position. If I am giving the size, let's say from here and at the center of here is 25 mm, and from here also from center, if the distance is 25 mm, so if it is moving, how much permissible tolerance we can provide it to this feature that the it should be not it should be functionally acceptable. Okay, so this is most important part. The true position is the exact coordinate. Okay, so in this case true position is the exact coordinate. Okay, so if I am moving, let's say this point is considering I am 0 comma 0. Okay, and the coordinates at the center of this hole will be 25 comma 25 for this coordinate tolerances if I am considering that. Okay, so that these 25 comma 25 is the exact coordinates or the location defined by the basic dimensions. Okay, so whenever we are not giving like this, so we are putting, I will show you in the steps that how we provide the basic dimensions. Okay, inside the box, or other means that represent the nominal value. Okay, in other words, nominal value is the exact value. Okay, I have already told you what is the nominal value in the geometric dimensioning and tolerancing or the dimensioning system. Nominal value is the exact value of the dimension. Okay, so in other words, the geometric dimensioning and tolerancing, position tolerance is how far your feature location can vary from its true position. Okay, so how much tolerance we can provide it to this feature, to this hole, that this hole is functionally acceptable, or it should be made with the other mating part. Okay, like shaft. Okay, so it should be like pin. So pin should be enter into this hole in the in the proper tolerances. Okay, so it is a related tolerance. Yes, the position is a relative tolerance. So we have to provide the datums. Okay, so primary datum, secondary datum, and tertiary datum, all three we can provide in case of positional tolerance. Okay, because it is a related tolerance. MMC or LMC applicable? Yes. Okay. So as we all know that if we are providing the tolerance to a feature of size, in this case, if we are providing for a hole, so it's a feature of size. Okay, to the axis, because axis of the hole is moving. So whenever we provide the tolerance to a feature of size, we can apply maximum material condition or least material condition modifier to the hole into the engineering drawing. Okay. So yes, we can apply the maximum material condition and least material condition. This is the symbol for the positional tolerance. So whenever we are making this symbol in the feature control frame, so first of all, in the first compartment of the feature control frame, we have to make one symbol. So this is for the position tolerance. Okay. Now here we have the now here with the help of we will understand that how we can steps to convert coordinate tolerance into a positional tolerance. Okay, whenever we have to convert a coordinate tolerance drawing into a positional tolerance drawing, so what are the steps we have to follow in the conversion? Okay, so one by one we will in the first of all what we have to do is give the dimensions with the feature of size, convert it to into basic dimensions. Okay, so the coordinate tolerance dimension, we have to convert it into the basic dimensions for the feature of size. Okay, I will let you know with the help of example only. The second step is position tolerance is a related feature. Okay, positional tolerance is a related feature. So we have to provide the datums into the drawing. Okay. Now the third step is we have to provide the feature control frame, because whenever we are converting coordinate tolerances into a geometric dimensioning and tolerancing positional tolerance, so we have to provide the feature control frame. Okay, now with the help of example we will understand. Okay, so this is the example. Okay, this is a coordinate tolerance example, and this is how we convert it into the positional tolerance. Okay, so where all the tolerances are given in plus one minus, in this you can see in coordinate tolerances, all the tolerances given in plus and minus tolerances, 100 plus minus 0.1, 50 plus minus 0.1 in this case also. Okay, so all the tolerances are given into the plus and minus tolerances. Okay, now we have to convert these tolerances into a GD&T. Okay, so how we can convert this into positional tolerance? Okay, so we all know that if you want to overcome all the shortcomings which we face into the coordinate tolerancing system, the positional tolerance is the only way by which we can come out of it. Okay, so the positional tolerance is something to get the position of the feature of size. So in this case, if we are talking about the axis, so axis is considered to be a feature of size. Okay, so to get the position of the feature of size, in this case, it is a hole. This is a hole. Okay, so here I want to get the position of this hole. Let's say, so here, then I have to use the positional tolerance to do so. Okay, so for this hole, these both the drawings are similar. So for this hole, first of all, we are talking about. Okay, so you have to convert the coordinate tolerancing system into a positional tolerance system. Okay, so what you have to do is there are three steps which I have already told you that involves. The very first step is give the dimensions. Okay, so if we are converting this into this, so first of all, we have to provide the dimensions. So 100 plus minus 0.1, we will similarly write into the drawing 100 plus minus 0.1. Okay. For this also, let's say 200 plus minus 1. In this drawing also, overall size we will write same 200 plus minus 0.1. Okay. Now, so the overall dimension remains same of the part. In the coordinate tolerancing system and the positional tolerancing system, overall dimensions of the part always remain same. So these are the overall dimensions, 200 plus minus 0.1 and 100 plus minus 0.1. Next is the coordinate for the whole. Okay, so you can see 50 plus minus 0.1 and 50 plus minus 0.1 are the coordinates of this whole. Okay, coordinates of the whole. When it comes to the coordinate, there is a small change. Instead of giving same tolerances, we have to put the dimension inside the box. Okay, so you can see this box. We have put these dimension inside the box. Okay, inside the box, which is called the basic dimensions. Okay, so this is the very first step, that we convert these coordinates into a basic dimensions. Okay, and put these without tolerances, we have put it this into the box dimensions. Okay, this is the first step. First of all, this is the first step to convert the coordinate tolerance drawing into a geometric tolerancing or the positional tolerance. Now, second step is in this positional tolerance is a related feature. Okay, we all know that the positional tolerance is a related feature. So first we have to provide the datums. Okay, in this case, datum, primary datum, A, secondary datum B, and tertiary datum C. Okay. So in this case, there are no datums. Okay. So in this coordinate tolerancing system, there are no datums. So I have to take three datums in this particular case. Okay. So the back surface, you can see the back surface of this part. So this is the, I will say this is the back surface of the part. This is the part side drawing. Okay. So this surface is taken as the primary datum. Okay. So I have written over A over here. Okay. Now this surface is, we are considering this surface of the part, we are considering it as datum B. Okay. And this surface of the part, the bottom surface of the part is considering we are datum C. Okay. So this is how we can provide the datums. In the case of primary datum, secondary datum, and tertiary datum. Okay. So now we have given all the datums into the part. So this is the second step. In the first step, we have converted the dimensions into the, for the coordinates of the whole, we have converted into the basic dimensions. So that is the first step. In the second step, what we have done is we have provided the datums to the part. In the third step, which is third step, is to give the feature control frame. Okay. So this is the feature control frame. In this case, you can see there are no feature control frame, but in geometric dimensioning and tolerancing, you can see that we have to give the feature control frame. Okay. So first of all, we will write down the positional tolerance symbol. So this, in the first compartment, we have written down the feature control, positional tolerance symbol. Okay. In the second compartment, you can see there is a tolerance. Now I will show you that how I have calculated this tolerance. Okay. Then there is a material condition modifier, because it is a related feature and we have provided the tolerance to a feature of size. So we can apply the maximum material condition and least material condition. And other three compartments, fourth, fifth, and sixth, third, fourth, and fifth compartment are for the primary datum, secondary datum, and tertiary datum, which we have provided into the drawing. Okay. So, so first of all, how do we decide this value? How do we decide this value of 0.28? Okay. So in this case, I will let you know that in this case for coordinate tolerancing system, the center have square shape tolerance. Okay. So in this case, you can see that it is plus minus 0.1. Okay. So the tolerance is of about 0.2 mm. In this case, also 0.2 mm. Okay. So there is a square of tolerance which is 0.2 and 0.2. Okay. So this is a square tolerance zone. This is a square tolerance zone which is 0.2 mm in this side and 0.2 mm this side. Okay. Now, how we calculate this 0.28? We have to, this is a 90-degree angle. Okay. So what we have to do is we have to measure this diagonal. Okay. So we can measure this diagonal, and with the help of Pythagoras theorem, okay, this as a perpendicular you can take, this is the base, so hypotenuse you can calculate. So in this case, the diagonal of this square is equal to 0.28. Okay, sorry, 0.28. Now what we do is we will make through this diagonal, we will make one circle in the tolerance zone. Okay. So in this case, you can see how we have converted this square shape tolerance into a circular tolerance zone. Okay. So you can see this tolerance zone. Now I have made the, with the help of this diagonal, I have created a circular tolerance zone. Okay. So this is a circular tolerance zone, which we have calculated over here. Okay. So now we get more tolerance. In red area, you can see this is the more tolerance we are getting. In this case, in the coordinate tolerance system, if the point lies over here, something here, x is over here, the part will be rejected. Okay. But in this case, when in the case of positional tolerance system, you can see when the part lies within the red circle, the part will be accepted. Okay. So that's why we are getting more tolerance in the case of positional tolerance, because we are using the diameter all over the circle. Okay. So 0.8, similarly, we are using this. as the positional tolerance. Okay. So this is the positional tolerance. We have converted the square shaped tolerance zone into a circular tolerance zone. With the help of this, we get more tolerance out of it. Okay. So here we have a, you can see this. So this is how we calculate the circular tolerance zone. Okay. So in this case, we have written over here 0.28 mm, or if we round off, okay, so you can use the 0.3 mm in this case also. So then ambiguous instruction for inspection is not required. Okay. So ambiguous instruction, we don't have to write notes onto the drawing for this. Okay. It is clearly shown that for inspecting the part, what we have to do is just if we have to measure this hole. Okay, so it is clearly shown that first of all we have to measure put the part with this side primary datum. Okay, and if I will tell you check the value of x direction to we get the different value. Okay, so in this case, if you measure the center axis of this hole, okay, so there are no datums in this part. You can measure it from here also, and you can measure it from here also. Okay, so both the things can happen, or you can measure it from here also, and you can measure the center axis from here also. Okay, so there are four ways. Okay, so somebody will measure from here or here, so the value will come different. Okay, so that's why to resolve this problem, okay, so we have provided the datum. Now if somebody has to inspect this part, okay, where in case of positional tolerance, if somebody has to inspect this part, if the inspection is done, so with the help of feature control frame, a person will dedicatedly know that first of all we have to put the part from the primary data. Then we have to check from here, from this position, because I have written over here, this is the secondary datum. Okay, so this surface is the secondary datum. So first of all, he has to measure from here. Then this is considered to be the tertiary datum. Okay, so then the person will measure from here the part. So it is clearly shown by this datums. In this case, there are no datums and there is a confusion of for the inspection of this part. But in this case, all the datums are provided. So we know that we have to measure it from the left side and from the bottom to top. Okay, so from left to right and bottom to top. Okay, so we cannot check from the other sides because I have take the two surfaces as a datum. This surface as a datum and this surface as a datum. I have already taken. So if I add over here maximum material condition modifier, because it is a we have provided the tolerance, positional tolerance to a feature of size, which is only the case. So we can provide the maximum material condition and least material condition modifier. Okay. So in this case, I have used maximum material condition. Okay. So I will get flexibility. Okay. Also, so if the part is produced at a maximum material condition, so in this case, maximum material condition will be 39.9. Okay. So if the part is produced at 39.9, the tolerance will be 0.28 or 0.3 if we round off this tolerance. Okay. Uh, okay. If the part will move from the maximum material condition towards the least material condition, let's say 40.1 will be the least material condition for this hole. Okay. So it will add up 0.48 will be the tolerance zone. Okay. So this is how we get the more and more tolerance zone with the help of maximum material condition modifier. Okay, so this is all about the positional tolerance. With the help of one more example, we will be discussing about in detail that how we can calculate the positional tolerance with the help of formula also. Okay, so this is how this is all about the positional tolerance system. And in the next discussion, we will discuss about the verifying the positional tolerance. So thank you. Thanks a lot.